Okay, so today we will talk about linear independence of functions, and let me explain why such thing matters. So here's an equation. Maybe I should title this linear independence of functions. Is it A or B? Independence.
That's right.
So suppose you have the following equation. Can you think of any solution to this? It won't be easy trying to figure such a function out, but think about it this way. If I move the y to the other side, basically I have a function whose second derivative is negative of itself. Do you have any experience in dealing with such functions?
Cosine, sine.
Cosine x, right? Sine x. These are functions whose second derivative is negative of itself. So we know that cosine x, sine x are a solution to this because second derivative of cosine is negative cosine, so it's going to satisfy that. And second derivative of sine is negative sine, so it also satisfies this. But are these all the solutions? That's always the question, right? See, I explained last time that after the second order differential equations, we changed the approach. Rather than trying to solve the differential equation, we tried to make guesses. We tried to make educated guesses, and by using these mathematical theorems about uniqueness and existence of differential equations, we can always justify whether we have all the solutions or not. Okay? So here's how it works. If you take any constant multiple of cosine x, would this be a solution to the differential equation? If you take any constant, what's the second derivative of this? It's exactly the same thing with the minus in front, isn't it? Cosine differentiates to negative sine differentiates to negative cosine. So you get the same thing with even with the C1 attached. And same thing with C2. This will still satisfy that. Not only that, we can add the two and still check that indeed this is a solution to the above differential equation. So let's try to see that this is indeed the solution to the above differential equation. So you differentiate once, you get negative C1 sine x, because the derivative of cosine is negative sine, plus C2 cosine x. And differentiate one more time, you get negative C1 cosine x plus, minus C2 sine x. And if you look at what this is exactly the same as y, except for the negative sign. So it's indeed same as negative of y, regardless of what value C1 and C2 is. Now this is very good because indeed the theory of second order linear differential equation says that if you have solutions that has two free variables, then you found them all. So that's basically the statement of the uniqueness and existence of differential equations. So there's some hidden mathematical theory behind the justification that this is all the solutions you have, which is rather too lengthy, and I don't want to do it here. So if you're interested, it deals with some function theory and fixed point theorem in function theory. It's very hard to understand. Okay.
Next question.
Yes.
Just to be sure, you're saying that to make sure you have all the solutions, you just multiply by constant.
I mean, we found that cosine x by itself is a solution. We found that sine x is by itself a solution. We found out that any constant multiple is a solution. Constant multiple is a solution. And then by inspection, we also added the two. And we found out that this is indeed a solution to this differential equation because we checked it. And then I'm saying that some mathematical theory backs up that this is indeed every solution that we can find. Okay. Now I'm going to make this in a more streamlined way, so you don't have to worry about what to do when you get these individual solutions. Right now I'm trying to introduce the theory. Okay. To actually solving this will be in the next lecture. Okay. So first, let me talk about some languages here. This here, right here, is called linear combination of cosine x and sine x. If it was some other function like e to the x, e to the negative x, it will be, I mean, whatever function you have, c1 times the first function plus c2 times the second function, it will be called a linear combination of the two functions. And sometimes it's also called a superposition of two functions. Sometimes known as superposition. Or linear superposition, linear combination. It's a way to come up with a new function from the old. Okay, so if you had two solutions, we're taking linear combinations of those solutions, and we check that it's indeed a solution. And actually, it will turn out that for any homogeneous differential equation, by homogeneous, I mean if you don't have any function of x by itself, any function of x should have y or y prime or y double prime, some y attached. And also, when these y double primes or y's appear, their powers should be 1. And never should these two be multiplied together. So those differential equations are called linear homogeneous differential equation. And for those, it will always be the case that if you find individual solutions and if you take the linear superposition of them, you will get the solution again. Okay, so yeah, but I'll try to explain why that is so in more detail later. Okay. Now, let's suppose that we didn't know this mathematical theory and somehow decided that maybe there's some more function, more solution to this. Okay? And said, by luck, we tried sine of 1/2 of x times cosine of 1/2 of x, and plugged into the left side by differentiating twice, and we found out that this is indeed another solution to the differential equation. Right? Actually, it's true. If you tried y to be this, and if you differentiate twice, you'll find that it's indeed the same as negative y. So let's see how that works. Okay, so y prime is cosine 1/2 x cosine 1/2 x times 1/2. I'm differentiating the first one. I should. It's a product of two functions, so I have to differentiate one, leave the other, and then differentiate the other, leaving the first, right? So that's what I got when differentiating the first one. And then, if I differentiate the second one, it's minus 1/2 sine 1/2 x sine 1/2 x. Where this time I'm differentiating the cosine. Cosine differs to negative signs. That's where this negative came from. And when you take the inside function outside and differentiate, you get this 1/2. Okay, so that's where I got that. Now let's differentiate this one more time. Actually, before we do that, let's simplify this a little bit. This is 1/2 cosine squared of 1/2 x minus sine squared of 1/2 x, right? And I also know that cosine squared of theta is 1 minus sine squared of theta. Looks familiar, right? It just means sine squared plus cosine squared is 1. Okay, so using that, I can replace this cosine squared of 1/2 x as 1 minus sine squared of 1/2 x. And because I have another one, I guess I can put a 2 here. So that's what y prime is same as. Or I can rewrite it again as what is it? 1/2 minus sine squared of 1/2 x. Now let's differentiate one more time, and you will see that it's indeed same as negative of y. Okay. All right. So differentiate one more time. 1/2 differentiates to what? What does this differentiate to? 0. Okay. How do you differentiate this one? Chain rule, right? 2 comes forward, so you have negative sine 1/2 x. Sorry, 2 comes forward. And times the derivative of the inside function, which is cosine 1/2 x. But then it's actually doubly nested, right? 1/2 x is nested inside the sine function, but sine is nested inside the square function. So I pull the inside function and differentiate it, but this 1/2 x has to be pulled out and differentiated again, which gives you 1/2. Now 1/2 and 2 cancels, and what do you get? Okay, and then is this same as what? What is this same as?
Y.
Same as the original y, right? So this is same as negative 1. Okay, so we saw that this is another solution to the previous differential equation. And this causes us some dilemma when we try to write down the general function, because look what we have here. Back to our original situation. We originally had, so recap, we originally had y double prime equals to negative y. So this was the second order differential equation we wanted to solve. And we found two solutions, cosine x, sine x. But then we found the third one, which was sine of 1/2 of x times cosine of 1/2 of x. So we basically have three solutions, and you'll see later that if you have any number of solutions of a linear homogeneous differential equation, you can always take linear combinations of them and come up with a new solution, and then this will be another solution. And you can check that if you differentiate this twice, you get exactly negative of y, but this is somewhat wrong because you have too many coefficients, right? You have C1, C2, and C3. So you have too many. Okay? So it's not good. So for example, the uniqueness theorem actually says that for second order, if I provide y of 0 and y prime of 0, those two values, then it's going to give you one unique solution. But because you have three unknowns, C1, C2, and C3, just having two conditions won't be able to give you the values for C1 and C2 and C3. Yeah. So this is not good. So here's the problem, or a headache. So problem. The above has too many functions. You should only have two, and seeing three makes us a little suspicious. So what's going on here? What's going on here? It looks like we have three different solutions to a second order differential equation, and we ended up with three free variables. But in reality, it's really just two solutions. So one of the answer is not really needed. What do you think?
Wait, so it's because there's a C3, that's what's wrong?
Yeah, see, it's a second order, so you should only have until C1 and C2.
Did you say C3 is like C1 prime or something? Is that
So really, this is nothing new. This is actually included in the previous one. So this seemingly different solution is actually another solution that you already have in disguise. Yeah.
So we have to get rid of the C3,
Yeah, but how? What's the justification?
divide by C3, and then...
No, not that way. I'm saying, can this be represented by any of the previous ones?
Is that it?
Yeah, so what does the double angle formula say?
Equals 1?
Cosine 2x.
No, the double angle formula for sine 2x. Do you know the double angle formula for sine 2a? What's that?
1.
No.
Sorry.
2 sine a cosine a. Oh, we're recording this. It's going to be on YouTube.
Sorry.
You gotta know things like that, okay? All right. So, for example, sine of x will be, according to this formula, twice of what?
Sine 1/2.
1/2 x cosine. So if you set a to be 1/2 x, then we know that sine x is twice of this. So what we thought was a brand new function that was totally different for cosine or sine was indeed just half of sine x in disguise. By the double angle formula, if you divide by 2, you know that sine half of x times cosine half of x is 1/2 sine x. Okay? So here's the problem in a more general setting. So suppose you have a general homogeneous differential equation and you came up with a bunch of solutions. How do you know if they are totally unrelated from each other? Okay. Now, look. Here's, I mean, you might say, well, just if you have enough solutions, let's just stop here and then don't worry about the rest. Well, that kind of makes sense because the mathematical theory already justifies that since cosine and sine are totally different functions, and this will be the general solution. But here's what can happen in a more serious way. What if your differential equation was y triple prime equals to negative y prime? Now, because this is just a differential equation obtained from the above, right? Just take this and differentiate both sides. You get this, right? So anything in here will satisfy that too. So if you differentiate cosine 3 times and compare with the first derivative, it's going to satisfy this. So this, all three will satisfy by this differential equation, right? And you might be fooled into thinking, hey, here's one solution, another solution, I have 3 solutions, and this is a third order, I found 3 solutions, we're all good. Okay? But there will be a totally wrong answer to this, because the correct one for this one is not that third one, it's actually just the constants. Constants will satisfy this equation because if you differentiate any constant, you get 0, so you get 0 equal to 0. Is that right? Y equal to 1 will be a solution to this because both sides will give you 0. Right? So what we have is that for this, we really want to say y is c1 cosine x plus c2 sine x plus c3 times 1, because 1 sine x cosine x are the really different functions, and you have 3 different ones. And if you chose this instead, it will be wrong. Okay. So it does cause some serious problems when we try to guess. Okay. So then there comes this notion of linear independence. So let's talk about linear independence. So definition. I'll just say definition 1 because this is not the desired definition, but it's easier to understand. If f of x is given by c1 gx plus c2 hx, then we say, let's put a quotation mark here because this is not really the definition we want, but it kind of will kind of make sense. Especially it will be helpful for the real definition. Okay? Then we say f of x is linearly dependent on gx and hx. So here's how we think about it. So as an example, e.g., sine of 1/2 of x times cosine of 1/2 x is equal to 1/2 of sine of x plus 0 times cosine x. Then we say this function on the left is linearly dependent on the other two. In other words, something that we thought was totally different from the previous one is actually representable as a linear combination of the other two. Now, if this happens, is that good or bad? If the another solution that you found was found out that it's a linear combination of the other two. Is that good or bad? It's bad because we want 3 independent solutions, or as much independent solutions as we want. Okay? We want different solutions, but if it's actually the same thing as the old, then it's not good. We haven't found all the solutions we want. Okay? So that's what we mean. But let me write down the real definition. If I move these two on this side, then we have the following form. If I call this fx, gx, and hx, it looks like c1 times f of x plus c2 times g of x plus c3 times h of x equal to 0, with c1 equal to 1, c2 equal to negative 1/2, c3 equal to 0, okay? So if this holds for some c1, c2, and c3, with possibly 0 values, but not all equal to 0. Then we say F, G, H are linearly dependent. You say these are all linearly dependent. And that's the case where we have to be careful. We want to avoid such a case. Okay? If we take the opposite of this statement, then we can define what's linearly independent. Okay? So still another definition. If C1 fx plus C2 gx plus C3 equal C3 hx, if three functions f, g, h are equal to 0, only when all of them are 0, but never in other case. Then we say FGH. Then we say FG and H are linearly independent. Okay. If the only way this can equal to 0 for 0 is when C1, C2, C3 are all equal to 0, then we say that it's linearly independent. And if we can come up with solutions that are linearly